Hey, Jules. Great, so if you came here today to learn about optimizing Spark SQL joins, you're in the right place, since that's the title of this talk. A little bit about me in terms of a background. I started in 2005 at Google. That's where I got my big data background. I worked on 2 products while I was there, mobile web search and voice search. Both of these, I ran clusters that were 1,000 plus nodes in order to pull things. So, for voice search, I ran MapReduces on 9 billion queries, unique queries in a year. And within the mobile web, I pulled probably close to a petabyte worth of data in order to build one of those mobile web indexes. So, while I was at Google, it was an incredible experience. I just came out of being a master's student, had a couple years of experience to be able to really experience what big data technology looks like. It was easy to use, it was easy to program, and incredibly powerful. I could get a ton done. After Google, though, I decided there were other places and other companies that were solving interesting problems, and I wanted to venture out and see what other companies do, and that's what brought me to Square to work on reporting and analytics. Also a data problem. Wanted to try a startup, wanted to see what that was like, and that really gave me the firsthand experience of how difficult it is for the rest of the world to do big data. So while I was at Square, I built reporting and analytics in 2012 on SQL databases, MySQL databases, while in 2005 I had big data, right at my fingertips. And that's what brought me to Databricks in 2014. My current job has been as a solutions engineer solutions architect for the last 2.5 years, helping customers come up to speed, learn how to use Spark, and educate people on how to make their projects successful. In my time at Databricks, Spark has really changed a lot. So the world in 2014, when I started at Databricks, Spark was 1.x, probably 1.1 or 1.2 or 1.3 when I joined. I forget exactly. The APIs that we worked on were RDD-based APIs. So again, a lot of that just writing raw MapReduce, like running raw maps, running raw reduces. And at the time, I gave a talk to kind of describe underneath what's happening, because when you're writing these APIs, they're meant to be easy to write. You're not necessarily thinking, how does this distributed system work? What's going on underneath on the hood? So that's when I did a talk called Every Day I'm Shuffling. Still one of my talks I've given that I really, really liked, because I think I found it gives a lot of customers the experience they need to know what's happening on this distributed system, which if you're not used to MapReduce and you just jump straight into Spark, sometimes you just don't get those fundamentals to see how that works. But let's fast forward to 2017, current today. We're now at Spark 2.x. Things are really different. Now people are no longer using the RDD-based APIs. They're deprecated. People are using data frames and data sets. There is Project Tungsten, which has made Spark run a lot faster. And more importantly, there's a very advanced Spark SQL Catalyst optimizer right now that knows how to take queries that you've written in SQL, plan how to execute them, and all of this stuff just kind of comes for free. So sometimes you don't have to think about it. And so that's a little bit of today's talk, is I still want you to understand what's happening underneath. Because if you write a Spark SQL query, most of the time the Spark SQL Catalyst is going to do well. But when it isn't, it's still really important for you to understand what's going on underneath, learn how to optimize it, learn how to look at it, and take a step back. So that's my talk today, is how to optimize joins. And when we say Spark SQL joins, it's just a simple select from a table, join table B on A.key1 equals B.key2. The topics that I'm going to cover today, in Spark there's basic joins, so shuffle hash join. We're going to go over that extensively because that's the most common join that Spark will use. And we're going to talk about troubleshooting cases as well. So if you run into troubles with that, you'll know when it works well, when it doesn't work well, and how you can work around that. The second kind of join we're going to talk about is the second most common join, which is the broadcast hash join. Also really, really important to know. These are the 2 joins that if you decide to fall asleep after the second half of the talk, if you got those 2, you're good. But I covered a few more special cases. Cartesian join, which I've seen happen more and more, which is pretty tricky to get right. And some special cases such as a theta join and a one-to-many join. Great. So let's talk a little bit about the shuffle hash join. So how many people have used the original Hadoop MapReduce kind of APIs and come from that world? Great. And then how many people have just jumped straight into Spark SQL? Great, so a good number, that's perfect. Because some of this will be good review and some of this will be totally new. So shuffle hash join is the most basic type of join, and it just goes straight back to MapReduce fundamentals. So if you understand what a cluster is doing, of how it does MapReduce, you understand how a shuffle hash join works. So the first thing in order to do a shuffle hash join is the Spark cluster is gonna map through both of the tables, just read in the data file formats for each one of those, and then it's going to create an output key. And the output key is the field that you're joining on for both of those tables. Using the output key, it's going to shuffle the data. So it's basically going to decide, it's going to take that key, it's going to create a hash on it, decide what final partition that key should go on. It's going to send it to that particular machine, and then it's going to sort and shuffle by that. So that's what we call shuffle. And then finally, we have something similar to a reduce phase, where we take everything with key 1 and key 2 that are equal in both of those tables, and then we come up with our final joined output. So a little bit more of a depiction on what that happens. It's again just a map, shuffle, and a reduce. So we have table 1 and table 2 that we're reading in by the individual worker nodes. We are sending them according to output, shuffling them according to the key that we're joining on, and then finally we're able to output our data. So that's a shuffle hash join. Does this look familiar to many of you? Great. And you know, if you just read through, there's obviously tons of different things. If you read back to regular old MapReduce, the shuffle hash join will make sense. So shuffle hash join in terms of performance, it works best when the data distributes evenly with the key that you're joining on. So you know, hopefully if you do a select with a group, select with your key and a count star and group by that key, you'll see that distribution is fairly even. And the other thing that you need for a shuffle hash join to work well is you need an adequate number of keys for your data set size. So, you know, if you have 2 million rows, you want to have, if you just have 200 keys or so, you'll never get more than 200 parallelism on that particular data set. So you want to have a good number of keys relative to your current data set size. Those are the two conditions you need for a shuffle hash join to work well. Okay, so I want to show you another use case right here, which is let's consider the case that we don't have these two conditions necessarily met. So in this case, I'm going to join two different data frames. One is everyone in the United States, and I'm going to join them on, I want another table that has information about each state. So I'm going to join on the state name of that person with the state's name. So here, we don't have those two performance conditions met. What we're going to see is we have uneven sharding and limited parallelism. So we start out where we have that US data frame. It's very, very big. And then we have this tiny little state data frame. We're going to do a shuffle across it. And what we'll find is we'll only ever have 50 keys for this data set size. And in particular, we're going to have certain shards, like California is going to have a ton of different rows, and on the other hand, Rhode Island there is going to have not very many at all. So your job is going to be bottlenecked by the amount of time it takes that worker node to work on that California data set, rather than having everything be nice and even. So, and what you'll find is, if you scale your cluster to more than 50 nodes, you're never going to get this to go faster because you don't only have 50 keys. So throwing a larger Spark cluster, it's not going to solve your problem or make this go faster. You can't throw money at it. And again, the problems are uneven sharding and limited parallelism. So I'm going to talk about the broadcast hash join, which does solve this problem later, just to describe what's going on there. And the broadcast hash join, it can address this problem if that small state data frame that we mentioned over there is small enough to fit in memory. So we'll go back to that. Okay. Let's consider some more performance optimizations with our shuffle hash join. So let's consider the case that we're looking at an RDD, or a data frame, for people in California, and we're going to join with all the people in the world on people in California.id equals all the people in the world.id. So I have some database that's state level versus world level, and I'm going to join on those particular keys. My final output size, it's only going to be proportionate to the number of people in California, so I shouldn't need that large of a cluster, right? That's not actually the case. And that's because, let's look at what happens here. So I'm going to have to map through at the entire California data frame and the entire world data frame, shuffle all of those data sets before I actually figure out that the majority of the data in the world data frame ends up getting dropped because they don't match when I do a left join to that California table. So in this case, uneven sharding is not a problem. Good parallelism, we still get that. If you get a larger size Spark cluster and you throw it at this problem, it's absolutely going to go faster. There's nothing wrong with this, it's just not very performant or optimal. So another way you can consider doing this is actually having more stages for your pipeline. Take the all world DF and already filter out the ones that have, come from the California state that you care about. And then once you have that smaller data frame, join that with a California data frame to create your output. So even though you have more stages in this particular pipeline, because you're using your cluster better, you're dropping the data as soon as you can, overall this is going to finish faster. So this is just an example to show you, if you have a Spark SQL join that's not going well, and it's doing a shuffle hash join, draw it out, depict how it's going to happen with your particular keys, explore the distribution of your keys for your data set. Maybe you can figure out why that shuffle hash join isn't working performantly for you. So, and again, what's the tipping point for huge? I can't really tell you. There aren't always strict rules for optimizing Spark SQL joins. Sometimes you just really need to look at the individual characteristics of your data set to figure it out. What the example I just showed you just now, if you only had 2 columns that you were considering, maybe that amount of data that you're carrying, since it's just 2 individual columns, is actually not that big of a deal, and you're okay just using it and dropping it. So it might not be worth optimizing if overall the query is still running fast enough for your purposes. So just understand your own data and its unique properties, understand how Spark works if you want to make it work well. Okay, so the other thing I wanted to show you a little bit is when you're actually running this job, how can you look at the Spark UI or look at different things to figure out that you might have a problem in your shuffle hash join. So one of the places I look is to go to the Spark UI, drill down to the job, drill all the way down to the task level, and then you'll get to something that looks like this here that I showed you with the task. You can sort it by status or you can sort it by runtime and look at it. So some of the things that I look for is I look at the runtime of the different tasks. If one task is taking, a few of the tasks are taking a lot longer to run than some of the other tasks, that's indicative that you might have uneven sharding. The other thing you'll notice is that Spark automatically sometimes will launch a speculative task. So that's if there's a machine that could go bad for a particular task that's running, Spark might try another machine in case it's just a problem with that particular machine that's making it go slow. You might see one particular task that's launching speculative tasks that Spark's trying to try the same task over and over again because it's taking so long. That's another sign that your Spark job might have uneven sharding or shuffle problems. And finally, if you look at the actual column that shows you the amount of input or shuffle output, you might see that it's different. And then another way to look at it is if you do just ls across the output files that you're creating, look and see if those are even, because those should be fairly even as well in an ideal scenario. Okay, great. So that's all I have for shuffle hash join. The next join that I really want to cover well is the broadcast hash join. So remember that case where we had a really large table on that little tiny table, and there was uneven sharding, there wasn't enough keys right there. You can actually solve that problem using broadcast hash join. So that's what we're going to do here, and I'm going to explain a little bit how that happens. So in this case, we're going to make this assumption that this small data frame is actually big enough to hold in memory. In that case, instead of shuffling all the data or other things, we're going to take that small data frame and copy it onto every single worker node on the Spark cluster. So that's what we mean by broadcast. And now when we go to the large data frame, every single partition, we can actually just look at the small data frame, which we've created a hash out of, and pull the rows from that small data frame there that match up with any row in my large data frame and output it. So broadcast hash join actually oftentimes, what you'll notice with broadcast hash join is the parallelism of the large data frame is maintained, so it's going to work great. We don't even need shuffle. So here we don't even need to transfer data across from one node to the other. This is going to work really well and performant when you do have a broadcast hash join scenario. It's often optimal over shuffle hash join, as I mentioned, since you don't have to do that shuffle phase. If you want to know whether the Spark Catalyst has chosen to do a shuffle hash join or not, you can use an explain command on your data frame, or even do a SQL explain command. And that'll output from the Spark SQL Catalyst what it's chosen, whether it's chosen a shuffle hash join or a broadcast hash join. If you're using Spark SQL table types like Parquet, the Spark SQL Catalyst should automatically make this decision for you. Sometimes if you're using an obscure Hive text file format of some sort, in order for the Spark Catalyst to make the decision that it should broadcast the table, it does need to know that the table is small enough to hold in memory. So if it hasn't computed that somehow because you're using some obscure text file format in Hive, sometimes the Spark SQL Catalyst may not know that. In that case, you might want to explicitly give it a broadcast hint, which you can do in data frame land to tell it what table to broadcast. Or you can just use Spark SQL Parquet, which is what we recommend as an optimal data file format. That Spark SQL will definitely always figure out for you. Okay, the next join that I want to talk about is Cartesian join, since I'm seeing this a lot more. So with the Cartesian join, you need to be really careful, just because it can easily explode the number of output rows you have. So let's say you had a table that just had 100,000 rows. If you do a Cartesian join against that table, you're going to end up with 10 billion output rows. So the number of rows you have is extremely large. The amount of data that you have is extremely large. If you look at the amount of input data that you have, you can go from 1 gigabyte to, what is that, like 100 terabytes of data, right? If you had that 100,000 rows. So Cartesian join, it can be pretty overwhelming. So I prefer sometimes to have more control over how a Cartesian join is working by doing a manual version myself. Because I find people, they don't actually need a table that outputs all the rows in one or the other. They're doing some kind of mathematical calculation that involves comparing one table from the other. So I have customers that they might be doing a linear regression of every single variable in a table against every other variable in the table. That's one example that I've seen. So to do that, I actually just use the regular RDD APIs here, and I'm going to generate all the pairs of UID by UID to generate that column. I'm going to be really careful about setting the number of partitions for that RDD so I can control the amount of parallelism I'm getting. I'm going to force a broadcast of all the rows in the table. So I'm going to have an object that's a hash table that, given that UID, gives me the row that I want to retrieve. Then I can create a UDF that, when I give it that UID and UID pair, it can look up the two rows of the table and perform a calculation and output that. So that was how I'd actually code up the Cartesian join. And you should be able to get that working. The next thing that you want to do is actually figure out the cluster size. So you need a really large cluster size sometimes to do a Cartesian join because you're just doing so much calculation. So the rule, having enough memory in your cluster to store the data in memory, it's not going to work for a Cartesian join. So what I do is I would try a small sample size of the Cartesian join that you want to do, and then time. If I know it takes me about this amount of time to finish 1 billion rows, then I know if I choose a cluster, if I want to keep that output time, if I choose a cluster with 10 times the number of nodes, that's how long it's going to take my 10 billion. So you can do a mathematical calculation to help you figure out what size cluster that you need. And I've seen customers, if you do a really computationally heavy computation, I've seen them need to spin up 100 node clusters, and they might need to stay up for 8 hours possibly to do a Cartesian join. And that's just because in order to process that 10 billion rows, that's how much compute power you really do need. So you can do it, just time it, size it carefully, and figure it out. Great. The next thing that I looked at was a one-to-many join. So this was a use case that I had. where a customer had a table, and then the second table actually matched on sometimes 100 rows with the other table. So in this case, it's kind of similar to the Cartesian join case where the number of output rows explodes, right, compared to my number of inputs. But what was interesting about this case that I just wanted to point out to you all is if you actually use Parquet to output your one-to-many join table, the size of the output files is not that much bigger than the input files, and that's just because encoding takes care of really compressing that duplicate data and storing it well. So, I was worried with the one-to-many join that the final size of my output tables was super large and it was going to create a lot of problems like writing and make it really slow. And I just found that Parquet took care of that all. So that was one thing that was really good to know. I didn't need to worry about or optimize as long as I chose Parquet as an output format. And then the final thing that I want to talk about is a theta join. So a theta join is the case where you're joining the two tables, but rather than equaling key A and key B, you're going to say, join as long as key A is less than key B plus 10 or some kind of range like that. When you do that, Spark is going to basically do a full Cartesian join. It's going to consider every row in table A and every row in table B, and then it's going to go through and it's going to go and try that condition on key A and key B. So again, this is going to be just as slow as a Cartesian join, and most of your outputs isn't going to work. Or most of your outputs are going to end up being dropped and not matching anyways. So with the theta join, what I suggest you do is you can create buckets on key A and key B, so you still have some kind of join condition. So you might say, you might have a certain field in A. You might even output A like 3 different times for a particular bucket. And then you can say, in order for key A to be against key B, I might have an additional bucket that I generated. Bucket A has to equal bucket B. And you might even have multiple buckets for table A. So as long as you can do that equal, again, you're going to narrow down the number of total rows that can possibly match. And that's going to make your join go faster. So I did this. I had a case where I had stock data, and I wanted to join it with, I had rows of stock data with certain dates, and then I only cared about matching on rows that were in a given week. So if I did just the stock symbols were equal, but the dates were within a 7-day range of each other, the theta join was very, very slow. But once I did something where, I picked a 7-day range or something like that to output, and I could also join on that before I did my theta join, my query went a lot faster. So great. And those are the different joins that I have today. I'd like to open it up for questions since we have about 7 minutes left.
Thank you for sharing the wisdom and knowledge. We got 2 mics on either side of the aisle. We got about 7 minutes, so there's loads of time for questioning. Feel free.
Hi, my name is Ani. I'm from Epsilon, and we use Spark SQL for further calculation in K-medias and stuff. And one of the instances was we were using a row number to calculate the ranks. And what we found is doing further computation on the data frame was rather slow. So is there a better way of calculating ranks on a data set rather than using a row number over partition?
So you're talking about a rank window function?
Yeah, or a row number.
Okay.
A row number over partition, order by maybe date or something.
I've seen cases, I don't know if this is your particular rank function, I'd have to look at it, but I've seen cases with rank functions where it was similar to the theta join, where if I created some kind of bucket, I could make that rank go a lot faster. So if you look at the query and if you can see if there's ways to narrow it down, that might work for you.
Okay. Thank you.
Gentleman on the right, go for it. No, you.
Me?
You're right.
Okay. My question was about custom partitioners and whether you have problems where that seems to be the right solution.
So, sorry, when you say custom partitioners, can you elaborate a little bit more?
Well, I was thinking of fixing the data skew. I mean, you talked about sharding as a problem, and you looked at the solution. that you presented, but if I had some alternate way of partitioning it other than by state.
Absolutely. So choosing a different set of keys to match on that's essentially what the theta join trick that I mentioned was, coming up with not just a primary key, but also a secondary key. And to make that theta join work, you might have multiple secondary keys for a given row for your first case. So if you can do things like that, that can definitely make things run faster. A really good example that I can think of is if you're building a language model. If you just were to use, when you build a language model, you're computing trigrams, and typically the key that you choose is the first word in the trigram. The word "the" appears obviously just way more than the given set. So the way that Google made this go faster, and they have a really interesting paper on it, is they computed unigrams completely separately, and then from then on they used bigrams. For bigrams, trigrams, or anything that they did, the output key was the first two words. And then even though the data set does not distribute evenly by just the first word, if they distribute the first and the second word, then it distributed very evenly. They were able to get around the uneven partitioning problem that way. So, be creative and clever and think of things like that.
Go ahead.
That was my question.
Okay. Well.
So it's from my understanding that Spark can, if the data is a little too large to fit into memory, can spill to disk and
Absolutely.
operate that way. We're encountering, joining two large tables. It's almost like a one-to-many join kind of a situation. And encountering out-of-memory and Java heap errors. Do you have any guidance do you just need a bigger cluster? Or do you need to think about the join more? Stuff like that.
Absolutely. So you don't need a cluster that's big enough to fit your data in memory in order to run on a data set. Spark can definitely spill to disk for your data sets. The Java heap errors that you're mentioning, it could be because your cluster isn't big enough. I've definitely seen that the case. I've also seen that case because the Spark configuration just isn't right, and I don't know how to fix that. We set really good defaults. Our open source team in Databricks takes a lot of care to optimizing those things. So what I would choose, though, is your data set sizes, they do need to fit in disk on a machine, and your biggest partition needs to fit on a single machine as well. So another thing that you could try if you are using Databricks is to use the storage optimized instances. So most of the time people, if you're doing SQL queries and you're doing aggregations, then using the R3 memory optimized AWS instances is a good solution. But if you're doing ETL, where your input data size and your output data set size are both very, very large, then those storage optimized instances can be very performant for you. So if you use that, I believe they're called I2 or I3 instances, that's a great one perhaps to try for your workload. And then you will definitely eliminate not having enough disk as an error or not for your use case.
Thank you.
Go ahead.
Hi. I have two very related questions to the number of partitions on the reduce side of the joins. So the first one would be, given that there is a default of 200 for the shuffle operations on Spark SQL, how does that compare to the different approach of RDDs in which you take the number of partitions from one of the two RDDs when you're dealing with big joins, big tables?
Great.
Definitely greater than 200.
Great. So that's a great thing to know about. So if you're using a really, really large table and you're not doing an aggregation, you're doing ETL on it, Spark SQL will choose a default partitioning size of 200. Mm-hmm. If your table's bigger than that and you have some reason to need it, you should manually set that to be larger than that. That's one thing you can try. So if you know your data set size is super large, tune it up to 1,000. And you may need a bigger cluster to take advantage of that, but you can try that. And you'll know whether you need to go from 200 to 1,000 if you look at an individual task, and you just find that out of your 200 tasks, when you only have 200, a task is taking super, super, super long. So try 1,000 and see if that works better. There's a new feature coming out as well
That was the second question.
that you can set. I forgot the name of the exact parameter.
Adaptive shuffling?
But what will happen is, what did you think the name of the?
Adaptive shuffling?
Yes. So there's a new feature that's coming out in the latest version of Spark that you can try. where it will actually size the number of out partitions according to the size of your cluster. So that way, if you choose a reasonable size cluster for your data set size, it should choose something. So that's something that you can try as well and experiment with.
Okay, thank you.
Anybody else? Well, please give a big hand to Vida. Thank you.